Hello everyone, welcome back to week 2, lecture 5. We will continue our discussion on fracture behavior of the materials. Today's learning objectives will we will understanding 3 critical parameters, Griffith's energy balance, we will understand what is a fracture process zone and how the temperature affect fracture mechanics or fracture behavior of the materials. So that's from a mechanics standpoint. And Griffith is approached this from energy standpoint. So in Griffith's theory in 1910s, he has published his first PhD thesis. And in that thesis, he argued the total energy of the system, it should be balanced. That should be equal to elastic energy of uncracked specimen minus the change in the energy caused by a crack plus the energy to create the surface. Or in other words, Griffith's theory is to discuss what he thought is a crack will propagate when the reduction in the potential energy that occurs due to the crack growth is greater than that equal to the increase of the surface energy. So if the reduction of the energy caused by the crack is bigger than the energy to crack the surface, so then you will have a potential energy to growth of the crack. So by looking at the energy balance approach, this is very easy to understand. When the crack grows, the energy is balanced, right? So the energy created by the new surface, it should be equal to the energy from the load applies. So if we apply the derivative over the crack size, so since this is no crack, right? So this is elastic uncracked area, so there is no derivative. So therefore here it would be 0. So as such, this derivative UA over the crack size A equal to derivative UY equal to derivative A. So that means the potential energy of the crack due to the crack growth, it should be equal to the increase of the surface energy. When this is balanced, that means it's stable. However, if this is bigger than the potential energy of the surface, is become very unstable. So that point is the critical energy point. So therefore, he rewrite this equation, the sigma, the critical stress, it should be equal to 2 square root of 2 gamma s times E A divided by pi. And then he introduced the new concept, G. It's called the critical energy release rate. So basically, it's how quickly the energy can be released from the material. So if that energy can be released faster, right, that means your energy and to create the new surface area is faster, so you can take much more stress. However, if that critical energy release rate is lower, and then the material cannot take much of. In 1957, Irwin has expanded this Griffith's theory from brittle material into ductile material by relating the stress near the crack tip to the energy release rate. So he is looking at it from energy standpoint and related to the previous mechanics standpoint. So therefore, he get this the very famous equation G1 equal to K1 square root divided by E. G is the critical energy release rate, as we discussed by Griffith's theory. Critical energy release rate. And again, K1 is a material's toughness or stress intensity factor, fracture toughness. and the E is modulus of elasticity, or Young's modulus. So basically, the critical energy release rate has built a bridge or defined a relationship between the material's fracture toughness is material's elastic stress or elastic stiffness, right? Young's modulus. So G1 is equal to K1 squared and divided by E. So this linear elastic fracture mechanics LEFM theory yield very reliable results in the field of brittle materials and ductile material, as been showing here. In the brittle material, because if you have lower K1C, the toughness, the fracture toughness, so therefore the critical energy release rate is low, so the tip can quickly grow the new surface area. In ductile material, because your K1C is high, so therefore you have a higher G critical or G1C, right? Your critical energy release rate is higher, so the tip can be blunt, and then you could take a large stress for the ductile material, and then the deformation the tip can be blunt, and then the deformation will be substantial. So linear elastic fracture mechanics works really well in the field of brittle material or ductile materials such as steel. However, it doesn't find very relevant to quasi-brittle materials such as concrete. For instance, in linear elastic fracture mechanics, you consider there is existing crack, and then there is non-cracked surface. There is nothing between. However, in concrete, there are many existing micro cracks that are individual cracks that may be situated near to the large crack tip. However, when the crack propagates, so if you have a concrete, you have a lot of a small shrinkage crack. So when the concrete under loading condition, when this crack tip propagates all those small shrinkage crack, they may propagate and merge, and then they become a very single large crack. And that become a single structure to give the continuity to the already existing crack. So therefore, we need some new theories, such as in this slide showing the fracture process zone, PFPZ, that's become important. So this fracture process zone will work as a bridging zone between the cracked region and uncracked region. So this is your cracked region, and then this is not cracked region. So this fracture process zone become a bridging, and then analysis of this zone would be deserve very special notice, because it's very helpful to predict the propagation of the crack and ultimate failure of the material such as concrete. So therefore, the Professor Bazin from Northwestern University in 1985 proposed this fracture process zone in concrete, and then based on his theory, the concrete is very important consider of the fracture energy, consider of the mesh size, and also size dependency, or people call it a size effect in concrete. Such as intuitively we know even the small component size, such as aggregate size, can influence the cracking of the concrete will be differently because of this fracture process zone, which we will not discuss in this lecture. So in general, we can think the material resistance will increase with the crack. So in this case, for instance, if I can draw the fracture resistance curve by looking at the different strain energy release rate over the time, and then the versus the crack, I can get this red color curve. So if I have a very low applied stress, the crack is stable. However, when the stress is increased, get into the sigma 2, and then they become a driving force, and then this crack started increase very quickly, and that's unstable area. So the AC, this is your critical crack length. So the entire fractal mechanics is to identify when the crack become unstable, when the crack reach the AC, or at what stress level, and this crack A0 will start growth, and then at what stress level this growth rate will become unstable. And so therefore, it's very important for us to use non-destructive testing methods such as X-ray diffraction, such as X-ray tomography, such as ultrasonic testing or ground penetration radar to identify the defect size and to understand if it's smaller than the critical crack length under the specific loading condition. So how we identify materials toughness, it's often tested by Sharpie testing or ISOD tensile impact testing. As been showing here, you lift the pendulum and to a certain height, and then use the pendulum to hit through the material, and then to see the material behavior and the stress. One thing it's important, I want to point it out, the material's fracture toughness is a temperature dependent behavior. So there is one certain temperature is very important, which we call temperature transition zone or brittle to ductile temperature transition zone, BDTT, brittle to ductile temperature transition zone. For instance, for A533 graded B steel, this temperature transition zone can be changed from actually 20 Fahrenheit. And once you reach to higher temperature, as you can see, material behave very ductile. However, at the lower temperature, material is very brittle. The energy absorption over the area is very small. And then it's grown substantially in this area. So in conclusion, in this lecture, we have discussed a lot of concepts. We have talked about fracture mechanics, and we described the role of the crack on performance of the material. We have talked about stress concentration factor at the crack tip, and then we discussed a flaw tolerance design, K1C, which is a stress intensity factor that equal to sigma C at critical times pi times the half of the length and the square root and the times F geometry factor. And then we discussed the Griffith theory from the energy balance standpoint. The energy needed to create the new surface, it should be smaller than the energy release rate. And then we talk about the plasticity and the process zone, which is very important for the material such as the concrete, quasi-brittle material with many existing cracks. And then we discussed the fracture toughness is a temperature-dependent material behavior. So as such, it's important to keep that in mind. With that, I will like to wrap up this lecture, and coming next is the viscoelasticity. Next week, we will discuss the viscoelastic behavior of the material.